gamma m0 v. And we call this the form momentum. Well, when v is very small, gamma becomes 1, and we just get the usual mv for momentum. So that tells us that in general, the momentum measured by a moving observer will be this times v, and therefore the mass a moving observer sees is gamma times m0. So that the mass increases as you look at it for a moving object.
So if you observe a moving object
Its
from
mass
different,
is greater than the person sitting at rest with respect to it would see.
so it'll vary with different reference frames.
Absolutely.
Weird.
Now, this is also the reason you can't make something go faster than the speed of light. I mean, you think, hell, I'll push on this thing as much as I want. You can't prevent me from pushing on it. And therefore, I'm going to increase the energy, and it's going to be going faster because it's 1/2 mv squared. But that's not what happens. As you put energy into it, m increases. So it doesn't go any faster once you get close to the speed of light. I mean, slightly, but the energy is not going into making it go faster, it's increasing the mass. Making sense? All right.
So if you're going that fast and you're traveling near the speed of light, your mass is increasing, so
and you push harder and harder, your mass gets bigger and bigger, but I don't go any faster, but I go slower.
But you would be like warping the space around you more and more, and so
that's
like,
right.
You
and that's
wouldn't
making
be
life
able to
very complicated.
You wouldn't be able to
Unfortunately,
go in a straight line as easily, right?
That's correct. Well,
because of like the matter around you.
well, okay. Now you understand the question he's asking, and we're fudging over into general relativity now. In special relativity, your mass is never big enough to affect anything. Remember, special relativity applies if gravity is unimportant, which means you weren't changing anything. Now, in reality, if your mass gets really big, then you're starting to warp the space around you, and then what you say is true. As long as your mass doesn't get to be very, very large, and large is determined by the equations in general relativity, and it has to be really big in order to have big effects. The sun, for example, changes the motion of the orbit of the perihelion of Mercury by about 42 seconds of arc per century. So these are small effects. And so for you, you would have to have tremendous energy, that is, be extremely close to the speed of light before you get the effect of you changing the space. And unless you change the space, as far as you're concerned, nothing is going on. I, looking at you, see you getting heavier and heavier and heavier and heavier. So we got, well, how do you go from momentum to energy? Well, you got to multiply by another velocity. The last thing we need is energy, because momentum is mass times velocity, energy is mv squared. So I'm going to multiply by another velocity, but it's got to be a constant. What velocity have I got that's a constant? Just one, c. Right. So,
John?
yes?
Does it make any difference what size the particles are?
No. Just the mass? Yes. Again, this is as long as we're doing special relativity time. So now I do another one. C enough they're not changing the space. Gamma m0 c squared. Gamma m0 c p. Okay. Now, this is gamma m0 c squared And remember, gamma m0p was the ordinary 3 momentum that you would measure. Mass times velocity. So this is C P. Okay? Now, let's look at this term for a second. Gamma m0 c squared. That is m0 c squared over 1 minus b squared over c squared. Square root. Now, let's look at this in the non-relativistic limit, where v over c is much, much less than 1. We know what we ought to get. Well, I'm stepping ahead here. Let's see what we get. M0 c squared. And now, if v over c is very much less than 1, then this is 1 minus x to the 1 minus a half. We know the binomial theorem we've used before. That's 1 plus x to the n is 1 plus nx plus higher terms. The usual Taylor series expansion for this. N is minus a half. X is minus b squared over c squared. So you get 1 plus 1 half b squared over c squared plus higher stuff. And so that is m0 c squared plus 1 half mv squared. In other words, that's our familiar kinetic energy. And so this term is the kinetic energy plus a constant. Right? And when you go to small v's. And therefore, since the origin of the energy, the Europlane, was arbitrary, this means that this quantity over here must have been energy. Because when you look at it in a non-relativistic, when you get to small v's, it reduces to kinetic energy plus a constant. And that is the origin of E equals mc squared. What we got is that the energy you have is some constant that was there whether you moved or not. That's the mass energy, E equals mc squared, plus whatever energy you add due to moving. And so, what we have is what's called the energy momentum tensor, which has, as we see over here, that which is energy, and c times p. This is energy momentum tensor. Or vector, energy momentum force. It's a tensor that we're calling a force vector here. So, what's the magnitude? If I take the magnitude of this, the length of it, I'm supposed to multiply it by its opposite vector. And so that would mean minus e squared plus c squared t squared is the length. And the length is the same for everybody. Right? And that's what's the same for everybody. In particular, it is the same as the person at rest with respect to the object. And for the person at rest with respect to the object, what is V? 0. It's at rest. What is gamma? 1. And so, what is the length here? It is E was this, gamma m0 c squared. And for the person at rest with respect to the object, for v is 0, this is just then m0 c squared squared with minus a. So we get a very famous result in relativity, that the square of the energy is c squared v squared plus m0 squared c to the 4. It's an equation you'll have occasion to use over and over and over, which you can derive from the Lorentz transformations with great effort, or from this trivial. Okay, now we're going to turn to the twin paradox. This was cultural. I mean, it'll be useful to you, but don't worry about it. But now you're just going to encounter that in the next part. Now let me explain what the twin paradox is. We're sitting here and we draw straws as to who gets to choose whether they take off on this rocket ship, travel around the universe, or they stay home on the couch watching jazz games. I win the draw, and so I choose to go off on my rocket ship. And so I want to be fairly comfortable about this. So I have this ship designed so it accelerates with acceleration of 1g, which I can easily stand. And I want to go a long ways. So I travel out for 10 years that way. And then I reverse the acceleration for 10 years. So I stop. And now I come back home. 10 years, 10 years, as I see it. So how long have I been gone as I see it? 40 years. Now you're watching this, and I'm going faster and faster and faster, and therefore you're seeing time dilation. So a year for me is much more than a year for you. So you see that I've gone more than 40 years. Right? But now I look back at you. What do I see you doing? Moving. So a longer time should elapse for me than elapses for you. Right? So when I get back, you have to think that I'm much younger than you, but I should think that you're much younger than me. Now I get off the spaceship, which one of us is younger? That's the paradox. That's right. But you see the paradox. Now, the resolution of the paradox is that one of us is accelerated and one of us is not. I cannot get back to the Earth without accelerating. I'm accelerating on the way out, I'm accelerating on the way back. That makes our systems fundamentally different. You are an inertial system, I am not. See the difference? Now we have to work out what that does. But that's why it is possible that we get that the answers initially appear to be paradoxical. Because the argument I was giving you was based on two inertial systems. That's where we got all this time dilation stuff. It was from two inertial systems. Well, there aren't two inertial systems. There's one inertial system and one non-inertial system. But does special relativity apply? Well, of course it does. It doesn't care who's looking at it. Only time it doesn't apply is if gravity is so big that it warps space. So we should be able to solve this problem. We just can't use the Lorentz equations directly to do it. Now, when I was a graduate student back in the Stone Age, people were debating vigorously this paradox. It wasn't understood. So the understanding of it is moderately recent. So that's because general relativity wasn't studied extensively until the late 1950s, because we didn't have the technology to do the measurements to test it. It wasn't until the 1960s and 70s we began to do experiments which really were accurate enough to test it. It's one of the amazing things about it, that you could have developed a theory which took 50 years before you could even test it. And it still turned out to be right. Okay, so how am I going to do this?
Professor,
Yeah.
do you feel the same way about string theory, since we can't test for things that small?
Yeah,
Or do you
I
think
do.
that should be
The
postponed?
difference is that in the case of general relativity, there were a few tests you could do. The motion of the perihelion of Mercury, for example. People thought we had tested it with the bending of light around the sun. It turned out that that experiment had error bars bigger than the result. So that wasn't really a test. But the precession of the perihelion was a test. String theory has none. And not only does it have none, it's hard to see any it could ever have. And so people are gradually losing confidence in this. As one of the people without much confidence says, it's not even wrong. You know, it can't make any prediction you can test at all, but not even a theory, because it's not testable. Okay. Now, how are we going to attack this? Well, what we're going to do is we're going to fill space with inertial coordinate systems. We're going to have an inertial coordinate system at every point in space, and traveling with a different velocity at every point in space. But each one is an inertial system. And at every instant of time, my spaceship is traveling with the velocity of one of those inertial systems. So I start out on earthbound inertial system. A year later, when I'm traveling at 9/10 of c, I'm going to be in an inertial system. I'm going to look at the system, at me, from an inertial system traveling at 9/10 c. Now, in that system, I imagine that I'm in there and I accelerate a little bit. Now, I'm going to look at the Lorentz transformation that would relate my motion in this inertial system when traveling at the speed I have at the beginning of an instant to the Earth. And I'm going to imagine that initially I'm running along at my velocity 9/10 c, and I throw something, my spaceship, forward with a velocity, the acceleration times some small time interval. And I'm going to look at the velocity then that would be seen from the Earth for my u plus v thing we did before. So what I'm going to do is use not two inertial systems, but a whole string of them. Am I making sense?
Yes.
Got the picture? At every instant, I have some velocity. Okay?
Is this
Now,
like
I have to describe things in that system.
Is this set up
And the
in...
description
Sorry.
is that I'm throwing a baseball, my spaceship, forward with some velocity, what? The acceleration I have times a little time interval. That's the velocity with which I throw my spaceship forward. And so now, as I see it, I have a velocity ADT, let's say. What happens down here on the Earth? I have the velocity of my inertial system, to which I add this ADT, but I have to do relativistic addition. The u plus v, 1 plus uv over c squared. So let's see how this would play out. velocity I would see at time on the Earth, you would see at the Earth at time t prime, plus dt prime would be let's draw a picture. So here's the coordinate system. Now here is the coordinate system which is traveling with speed v at t prime. T prime are the clocks in this system. Okay? Now, let's suppose the acceleration as seen by the pilot here in his time is a of t prime. Okay? And he throws himself forward with a velocity u prime, which is a of t prime t prime. That's the little incremental velocity, and he throws his spaceship forward with this. Okay? Now, I want to know what is the velocity that I am going to read from this system when that occurs. Okay? Well, I know how to add velocities. It is v of t prime plus a of t prime divided by 1 plus v of t prime u, which is this, a of t prime dt prime divided by c squared. Now, what is v? Well, v is the velocity that this ship had with respect to v, and that is v of t prime is equal to u of t prime. Because the v is the velocity that this ship has at time t prime. And that is u, because I'm trying to measure, u is the velocity that the ship has. I'm finding it at t prime plus d prime plus dt prime. Well, at t prime, it was traveling with the velocity this ship has, which is u of t prime. Did I make that clear? Sounded pretty fuzzy to me. Did it make sense?
Maybe just summarize.
Let's try it again. The velocity the ship has, as I see it from the Earth, is u of t prime. That's the symbol I'm going to use. That's the velocity the ship has as I see it from the Earth. Okay? Now, I want to know what its velocity will be at time dt prime later. Well, what I'm asking then is, I'm looking at a system that's traveling with velocity u of t prime down my x-axis. In that system, somebody throws an object forward with a velocity this. That's the acceleration times the time in this system. That's the speed with which the rocket ship is going to be thrown forward relative to this inertial system, which happens to be traveling with the speed my ship had at time t prime. So I have to add, to see what I'm going to see at this later time, I have to add what I had originally, the change, and divide by this. So this v is actually u, and this v is actually u. Okay with people? So I change this to a u of t prime, and I change this to a u of t prime. And now I multiply both sides by the denominator there. And I get u of t prime plus dt prime plus u of t prime plus dt prime, u of t prime, a of t prime, dt prime over c squared equals u of t prime plus a of t prime dt prime. Now, I bring this over to here, u of t prime plus dt prime minus u of t prime. And I bring this over to the other side, equals a of t prime dt prime times 1, that's that, minus u of t prime plus dt prime times u of t prime over c squared. Now, I divide both sides by dt prime. And so I get u of t prime plus dt prime minus u of t prime divided by dt prime equals a of t prime times 1 minus u of t prime times this. But what is that? By the definition of a derivative, that's u of t prime plus du dt prime times dt prime over c squared. Now, I take the limit at which dt prime goes to 0. That converts these things to derivatives. And so I have du of t prime dt prime equals a of t prime times 1 minus u of t prime squared over c squared. And this has a dt prime left, so it's going to go to 0. So, lo and behold, I have a differential equation that will give me u of t prime as a function of time. Make sense? All right. So, that's easy. I can do that. I'll have u of t prime divide by this. Our usual procedure, put all of one variable on one side, the other variables on the other side. Equals a of t prime dt prime. So now, I integrate from the 0, where I started, to u of t prime. I integrate from 0 to t prime. And that will give me u as a function of t prime. So now, we go to the Greek monster, and we look up that integral, which is of the form dx over 1 minus a squared x squared. Let's throw away a pen here someplace. Okay. Square root. That's straight. Okay, here we go. So, the integral is, of that thing, is get C times the hyperbolic tangent inverse of B over C. So you get U over C. That's the integral of this thing. Evaluated between 0 and equals this integral. A of t from 0. And so, what you get is, so this gives you hyperbolic tangent of of 0. Tangent hyperbolic is sinh x over cosh x. And this was e to the x minus e to the minus x, e to the x plus e to the minus x. And when x is equal to 0, that's 0. So, the hyperbolic inverse tangent of 0 is 0. So what you get is times integral 0 t prime a of t prime dt prime. And now take the adjunct. And so you get u is equal to the integral from 0 to t prime you get c times the hyperbolic tangent of 1 over c, integral from 0 to t prime, a of t prime, dt prime. So that's good. So now let's put in our particular case. And our particular case is let's do it for the first 10 years. And so for the first 10 years, we had a of t prime is seen by the pilot, it's just g, acceleration of gravity. And so what we get is u is c times the hyperbolic tangent 1 over c integral 0 to t prime g dt prime. And that is just going to be g times t prime. So we get c tanh of g t prime divided by c. So that gives us the velocity in the prime system. Okay? Now, how much time elapses on the Earth during this time period? Well, we know time dilation. We know that in a time dt prime as seen by the pilot, who's at rest with respect to himself, a time gamma times dt prime will be seen from the Earth. The delta t on the Earth will be the integral from 0 to t prime of gamma dt prime. But that means it'll be the integral from 0 to t prime of dt prime over gamma, which is 1 minus u over c. That's beta. Tanh squared of g t prime over c. Square root. All right, now from the handy dandy faster. We find that you can work this out just from the definitions, but I'm being lazy. 1 minus tan squared is equal to the hyperbolic secant squared. But that is 1 over cosh squared. And therefore, when you take the square root, you get cosh. And so you end up with the integral from 0 to t prime of hyperbolic cosine of g t prime over c dt prime. And that's an integral you can readily evaluate. The integral of cosh is sinh. And so what you end up with is c over g hyperbolic sinh of g t prime over c, the value between 0 and t prime, where the sinh of 0 is 0. And so the time passed on the Earth is c over g sinh g t prime over c. Where this is the time passed on the rocket ship. Now, you can do this all the way out, down, back. It turns out to be 4 times this one answer. Now, you put in numbers for this. And let's see what we get. I do it just for 1, then we'll multiply by 4. And c is 3 times 10 to the 8. This is 9.8. This is the sinh of 9.8. 3 times 10 to the 8. And t prime was 10 years. And a year, it turns out, it's a numerical accident, but it's very, very close to pi times 10 to the 7 seconds. Just multiply it out, 365.25 times 86,400. This is right to the 100%. And now, you do the arithmetic. Just calculate what this thing is, and what you get is get 4.38 10 to the 11. Seconds. And you divide by pi 10 to the 7. And you get 13,700. And now multiply by 4, and you get about 53,000 euros. So that you've been gone 40 years in your time, and on the Earth 53,000 years of yours. One G isn't all that much. 40 years is a long time, but it's well inside a lifetime.
So there's all sorts of different aging things in the universe at different rates. Weird.
Now you have to ask yourself the question, how would you find how far you traveled as seen from the Earth? How far did you travel as seen from the spaceship? Now, you know that the ultimate result has got to be the same. So, as seen from the Earth, you traveled a long time. You must have gone a long distance. As seen from the spaceship, you traveled a short time. You must have gone a short distance. So how can you be at the same place in the universe? Because as seen by the spaceship, what happened to the distances in the universe?
Contraction.
They shrunk. So you think you went 20 light years. The Earth thinks you went 200 light years. But lo and behold, where it was 200 light years to star squawk, as seen from the Earth, it's only 20 light years to star squawk, as seen from the spaceship. So you both think you reached star squawk, but you think you did it in different ways. A long distance after a long time, a short distance after a short time. Now, on Monday, I'll work that out for you. But you should play with it between now and then, see how you can do it. You have everything you need to know. But anyway, so that's the twin paradox. Did that make any sense at all?